I think it's time. Let's start the webinar now. Over to our CEO, Mr. Thomas Lindqvist. And Thomas, remember to unmute.
Hello and welcome everybody. It's nice to meet you over this webinar. Yes, my name is Thomas Lindqvist. I'm one of the founders of the company. So been in this business since '94, starting at ABB, the marine automation team, working as different roles within ABB Group. Left ABB in 2010, and since then we're focusing on this energy efficiency for large ships. So over to Per.
Thank you, Thomas. And yes, we are broadcasting today from Västerås in Sweden. It's winter here. We had minus 17 degrees yesterday. It's a little bit better today, but the winter is really here. So I'm not a mariner. I'm a software guy, but I've been providing solution to the maritime sector. Started in 2006 by launching a new high-speed navigation system for high-speed crafts. And then after that, I've been working as a CEO for a company that developed a product called EnviroManager, a position-based information system for environmental regulations, a system that is used on close to 5,000 vessels globally. So I've been working in QTAG since January this year. So we'll take us through the agenda of today. So this webinar will inform you how you can save more fuel by combining weather routing and power planning. And we're going to look at a case study, the vessel Kaitaki, that by doing that is using 13% less fuel, which is quite amazing, I think. Thomas is going to take us through the core principle of EcoPilot, our fuel saving systems. And then we're going to look at some implementation examples and expected return of investments for that. So all of this will take around 20-25 minutes, and then we're going to save 5 to 10 minutes for questions at the end. Okay, so let's look at the case study for the vessel Kaitaki. We had a trial during 3 months period for a Kaitaki that was going between Picton and Wellington. In total, 246 crossings during a 3 months period. This is the minimum that what you need on board from our system. You need to have the EcoPilot panel PC for the user interface. We have to bring in some engine data and an EMEA data, of course, to see what is affecting the vessel. We have an app server where the brain is our system, and then we have an echo server where we have the digital twin, and you can see the result of we have connection to the internet, of course, also. So we have to bring in some weather data, and we can send information on the shore side. And the result of this trial was quite amazing, I would say. On the crossings, when manual crossing, when EcoPilot was not activated, we had an average fuel consumption of 5.9 metric ton for this voyage. And when EcoPilot was activated, looking at Picton to Wellington, we had an average fuel consumption of 5.2 metric ton. So a total fuel saving of 11%. And looking at the other way, Wellington Picton, we also decreased the fuel consumption with 15%. So in total, using EcoPilot, we have a proven fuel savings of 13%, which is quite exceptional, I would say. So the question is, how do we do this? And Thomas, I will hand over to you, and you are in control of the slide.
Okay, thank you so much, Per, for the introduction. And let's see if I can scroll down. Okay. All right. So now I can control also, which is important for the control of the ships. So as a known fact, for the fuel consumption of ships, there are a number of parameters that affect it. The number one is, of course, the ship speed, so an acceleration of the ship. And then you have a number of other external factors, such as the weather, sea conditions, wave tides, currents, obviously loading conditions, the draft, the trim of the ship, propeller optimization if you have a CPP type propeller. Also a number of engines. If you have a ferry with 2 or 4 engines, you can have different setups with that. Or hull performance, as that changes over time after dry dock. And then finally, traffic situations. There are other ships you need to look out for. So there are a number of things we can do. We can affect the speed, we can change the propeller pitch RPM ratio, and we can control the number of engines. There are a number of other items that we can't really control. The weather, loading conditions. I mean, you have the cargo that you want to transport, hull performance, and traffic situation. So what we can do is that we can actually help the captain to take good decision and work with these external conditions. So one famous scientist, Niels Bohr, said once that prediction is very difficult, especially if it's about the future. So even though you know all these factors, what affect it, you have a weather forecast, and the only thing you know that's not going to be true. So how do we handle all this? So I've prepared a couple of examples how we do this in the system. So the first
Thomas,
is
we're just one thing, we are requested to speak a little bit louder. So
okay,
yeah.
I'll try that.
Okay.
Okay, to start with, there are 2 options when looking at optimization of the propulsion. One is to go with traditional, which is typical offline optimization package do, that you come up with a proposed fixed speed of the propeller. And that is good. I mean, it's better than nothing. The problem with that is that even though you keep a constant RPM, due to the effect of the varied wind, waves, current, and so forth, you will have a varying required torque out from the engine. So that means that the propulsion power will actually not be constant. It will vary. By keeping the constant RPM, you have different. You need to have different torque out from the engine, and then you have a varying propulsion power. What we do in our system is...
One question there, Thomas. Couldn't
Yes.
it be under some conditions where fixed RPM is really the best way?
Absolutely. And that would be, of course, the sunny, nice, the sailor's delight days.
Okay.
And there are no external factors that are really affecting the ship.
So no wind, no waves, no current. Then
Exactly.
this could be the optimized way of sailing.
Exactly. So we're all looking for those days. Okay. What we do then is looking at how can we go with even though the external factors are changing, how can we go with a fixed power instead? So that means that we always keep track of the torque and RPM to keep a constant propulsion power. And that is the most efficient way to take a ship from point A to point B, or car. So one example then, in this case, that the RPM will actually vary over the voyage automatically by our system. Ship speed will also vary a little bit due to the external factor, but this is the most optimum way to take the ship from point A to point B.
This is really interesting because, and as you say, you can try this on your car. If you put your cruise control on your car on a fixed speed, it's a fixed RPM, and then you can actually hear how the engine is working more when you go uphill. And compared to, I've been doing this test when I go to this office, and then I was doing it manually instead, actually going a little bit slower when it was uphill and actually a little bit faster when it was downhill. And to my surprise, the fuel consumption the difference was almost 20% actually. So it's clear that fixed RPM is not the optimum way to go if you have if the resistance is changing over time.
Yeah, that's very interesting. So to everybody can try that today when they go home. Okay, so the mission then for our system is to find the lowest possible propulsion power while still meeting the requirements and still arriving the ship on time with the given parameters that you have for your voyage.
Thank you, Thomas. And let me take us through a little bit how the system and the different goals you can have in the system. You can have arrival time or CI value. There are some other modes you can choose between. And of course, we have to bring in data into the system, the planned route, your weather planned route, the weather forecast. Again, a forecast is just a forecast. The only know about the forecast, it will not happen exactly as a forecast. The outcome will differ. And that's why it's also important for us to bring in constant ship data and engine data and adjust to the real situation on the vessel. So it's important to know that this is not an advisory system that tells you what to do. This system is in control. We are controlling this and is doing the adjustments in real time to really, really make sure that we're using a minimum power for the route. So we have the optimized power plan calculated, a high resolution power plan, and then the system is controlling everything. And then there's other, of course, ways to optimize. If you have a pitch propeller, you can have the combination between the perfect RPM and the pitch of the propeller. This high resolution power plan, you can't really let a captain make this small adjustment that our system is doing. He would have to have his hand on the telegraph system all the time. So you can't really compete to a machine in this case. So the system, our system is executing the perfect and calculated power plan through this engine control. And Thomas, I let you give an example of a voyage.
Yes, so we prepared an example of a voyage. It's sailing from Yalova outside Istanbul to Sète in outside Montpellier in France. In this prepared example, there are two alternatives. One is the shortest route, which is through the Messina Sound and then between Sardinia and Corsica. And then we have the west route going south of Sicily and south of Sardinia. Based on the ship model that we have and based on the weather forecast, the wind, the sea currents, sea depth, and so forth, we calculate the estimate fuel consumption for the full voyage, 183 ton for the shortest route and 212 ton for the western route. And also we see that by taking this normal route, we get the CIC rating. And if we take the other route, we will have a D rating. So obviously the captain will take the C rating route to comply with the new regulations and save fuel for the company. But as you know, the only thing we know, things will change. So the first thing that happens is that there is a queue in the Dardanelles Straits. So now we have a planned arrival time at the entrance at 4:02, but and we have a planned sailing speed of 20.7 knots in the Marmarian Sea. But as there is queue, we get the delayed 15 minutes. So we have a spot at 4:20. Immediately the ship speed will be reduced 1 knot roughly. And that of course saves fuel and that passage. But then for the remainder of the voyage, after coming out of the Dardanelles Strait, we'll have to increase the speed. But of course, that's a much longer stretch. So the speed increase is quite small, actually. So this is one practical way how the system helps the captain to always go as slow as possible or with the minimum propulsion power as needed. In the graph you see here, the green is the ship speed, gray is the sea depth. We have a sea depth map for the whole world, and red is the power plan. So here you see there is a speed restriction in the Dardanelles Strait, and the passage here it's very slow, 12 knots. And all those things are taken into consideration in the power plan, just to help and control, actually, to reduce the speed during that passage to avoid penalties. So next thing that happens, pilots are on strike in Messina Sound. Not good, because that means that we have to take the longer route, the more expensive route. And as you know, remember, that's a derating route. So what do we do then? I mean, you have to take a decision that it's okay, we can go with the zero, keep the arrival time at the 2300. Or you can take a management decision and say that, no, actually, we're gonna delay the arrival with 3 hours and keep our C rating. But then again, that's a practical way how we can help shipping companies to take conscious decisions that we stay on C or we accept D, and it's not just happening. So this is a practical example how the system helps by keeping all the time an optimum plan and implement that automatically. All right, Per, over to you.
Nice, Thomas. So the system is really executing what you would like to do.
Yes, that's the idea. Captain's best friend.
Okay, I'm going to take us through some implementation examples. We'll have a look at an older vessels compared to a newer vessel and what return of investment you can expect from doing that. So this is a little bit older lady. Kaitaki was built in 1995. We did a little bit more than just implementing our system. We also exchanged the analog governors with our digital governors. We are, since many years, been the provider of governors to ABB. So on several hundreds ships out there, it's actually our governors. We also replaced, or they need to replace the actuators. We are also manufacturer of actuators. Both ABB and Wärtsilä is actually using our actuators. So if you are doing retrofits of governors and actuators using ABB or Wärtsilä, it will be our equipment that will be installed. We changed the panels, so you can say that even if it was a complete retrofit, it was a cost of 370,000 euro. Thanks to taking an additional investment of our fuel saving system, because if they didn't do this, would have been sunk cost. They also installed EcoPilot, and fuel savings with EcoPilot is around 750,000 euro per year. There is an additional, we need to make some money in the long run as well, developing our software. So there is a software license cost that is a percentage of achieved fuel with an upper cap, unfortunately. Otherwise it would be good on this vessel. So how does it look on a newer vessel? What do we do there? If we look at the vessel that is built in 2019, then it's enough to provide these parts of the system where we are bringing in the NMEA signal. We're integrated to the bridge control system that we are using our controller and communicate to the existing system. This system doesn't take several weeks to install. This takes about two days to install, actually, on the bridge. And return of investment is usually around 2 months with this, and you can expect fuel savings of around 200,000 per year if it's a fixed propeller. So that is the minimum we can see, around 3 to 4%. Normal fuel savings, I would say, if you have a pitch propeller, is between 6 to 8%. What we did with Kaitaki, 13%, is very much due to the extreme conditions that they're having. It's a lot of current, a lot of changing condition at all the time, and we can just see that EcoPilot is much superior to the human being and during those kind of conditions. So I think we've been spending our 25 minutes, so there is questions and answers coming in.
Sure, we have a few questions. Let's see. The examples used passenger ships. Is this a solution for Ro-Pax and Ro-Ro only?
Thomas, what do you say? How many different vessels have we installed this on?
Yes, I mean, we have installed it on bulk carriers and tankers as well. And obviously there is the benefit with the Ro-Pax ships is that they're going on the same trade all the time. That means it's very easy to verify the savings because you can compare so many voyages. But the installation and the technology and all that works exactly the same on longer routes, like the one I showed from it's not a long route, it's 3 days from Istanbul to France, but still it works for all type of ships. So there's it's a very versatile solution in that way.
Right. Another question, is retrofitting possible? And if yes, what's the need for the virtual telegraph?
You can.
I'm reading, Thomas. Could you please?
Okay, yes. So what's needed for this is that we need to have an interface to the existing telegraph system. And a good thing is that there are normally, like today, we have solutions for Quant, which is a very popular telegraph system, and for Wärtsilä Nacos Platinum system. So, and we are developing more as needed. So it's very, it's quite standardized, and it's very good to do it in a safe way and also according to class requirements. So that's important for us, as we always have our products marine type approved.
Thank you.
I also have a question here, Thomas. Maybe you can answer this one. It's about the 13% that we claim on Kaitaki. What was the baseline and the condition that created this baseline when we made the comparison?
Yes, as all good ship owners, they keep an eye for each voyage on the fuel consumption, so they take records. And so they did their own independent comparison also before and after starting to use the system, so they could see actual numbers on this. So that helped also to have a verification second eye on the numbers, which is what we prefer, if possible, that if the ship owner has some own engineers that can do that verification, that's the best for us. So, yeah.
Okay. I have another question here. How much extra will I save by using EcoPilot on top of weather routing?
Yes, the way we can look at it, weather routing is great, especially for long voyages, let's say across the oceans. Then the power plant will save another 3-4% according to what we see. But easily, if you have changing conditions, let's say that you have a new slot in the next port, the savings can actually be 10% or 50%, but that's more operational. And how do we save more compared to that? Typically you get an email maybe every 24 hours from the weather routing service to change or something. Here you can communicate from your shore connection and more or less in real time give the captain an update to accept the new arrival time. So that's obviously that's a save of maybe 10-12 hours on average to slow down the ship. If you have another, let's say, delay of 10 hours, you can immediately slow down half a knot, and that saves a lot of fuel. And then the saves can be tens of percent or in that range.
So really what we've been looking at and presenting for Kaitaki is actually the technical savings that we're doing by calculating this minimized power plan and being able. There is also one more that I can see from our customer, cruise ships. When you have this on cruise ship, you have a timetable to follow. You must be on time. It is in the human nature that you go too fast in the beginning to have a buffer at the end. And with our system, you avoid that. It will take you, you will reach your estimated time of arrival with +- 3 minutes, I would say. That's what we are generating with our system. And that could also generate lots of percentage in savings as well, because you can never win back that fuel that you're losing in the beginning by going too fast.
Yeah, and another aspect is that obviously the captain is the most senior navigator on the ship, and he can set up the system the way he wants the ship to be run. And then he has the junior guys on the graveyard shift during the night. They have a system that actually runs the ship as if the captain would have been there. So that's also a benefit, that you always have the captain's decision implemented on the bridge. You know?
Okay, I have we have time to answer one last question. What is the commercial losses due to the reduction in speed that occurs when we keep the same power/consumption?
Yeah, obviously, there are party charter agreements that you need to comply to. So over 24 hours, you will need to keep an average speed, and you need to keep the performance of the ship, the fuel consumption. So over 24 hours, we will keep the ship within those charter party agreement boundaries.
Yeah. So exactly, again, you can decide what ETA you need to reach not to have any commercial losses. And again, we will bring the ship from A to B with the minimum fuel consumption. And of course, there is other boundaries or conditions that you have to fulfill as well, that we can also make sure that they are fulfilled actually with the system.
Yeah.
So we have
actually, if you do things right, there should be less commercial losses.
Absolutely.
Better control of everything.
Yeah. I'm very happy that we got so many questions, but I also promised that we shall keep this webinar time in 30 minutes. I will gather these questions and make sure that we answer them and send the questions and answers out to everybody that has been participating today. So from me and from Cold Västerås, I would like to say thank you, everyone, for participating, and watch your email box. We're probably going to send some new invitations to webinars also in the beginning of the next year. Thank you very much.
Thank you.
Thank you.